We are going to start in a minute. If you want to take place, please, guys. Okay. Are you ready? And now we have Sébastien Bratières that we talk about foundation model for speech. Welcome, Sébastien.
Thank you, Cesare. Yes, I want to tell you about foundation models for speech. I'm going to tell you about a couple more things before we get there, just to give you context about why I'm doing this and where I'm doing this and all the stuff around that. The first thing I want to tell you is about myself and why I'm interested in foundation models for speech. So I grew up bilingual in German because of family ties and everything. I'm French, so my other native language is French, and then there's German, and then I learned English on the way and some Spanish, and at last I learned Italian. So I grew up interested in language from childhood age on. So I was reading grammars and dictionaries before it was healthy to do so, I guess. And then growing up as a teenager, I was interested in science, especially in engineering, because science is nice, but engineering is better, I think, because you can build things when you're an engineer. And so these were my two, the two things, the two areas I was interested in. And so when I got the opportunity, I studied engineering then in the end, and when I got the opportunity to bring the two together, I decided to take it. And that was when I did a master's in natural language processing back in Cambridge at the time. So I finished my studies in engineering and went for computational linguistics essentially. And then I worked for some years in the industry doing speech recognition systems, embedded ones for like logistics and maintenance. That was back in the early 2000s. Telephony systems as well, speech-driven telephony platforms, the early things that didn't work. And a couple of years later, they started working. And then I went back to do a PhD because I thought this was the thing I wanted to do, so I had a good taste of science doing the PhD. And I decided I'm going to do my PhD not in natural language processing or anything, but in machine learning specifically. Because I felt like stuff was happening in machine learning, not in an LP, as like the engine, I was feeling the engine was in machine learning. And I guess part of what happened next proved me right, so I'm really happy I did this choice. And so these days I work in these things. One place, so I work in several places, in mainly two that I'm going to speak about now. Translated, that's the company I represent today, so I'm the director of AI at Translated. Translated is a translation services provider, so we sell literally the translation service. You come to us, you have, say, a document, you upload it, we do a quote for you, you accept the quote, we machine translate it first, and then we send it over to a professional translator who will post-edit the machine translation. Presumably there's going to be a second translator reviewing the entire thing before it goes back to you. That's the service we sell to you. So Translated has been in existence for like 20 years now, and it's mainly a pure internet, an online service for 20 years of its existence, while many of the other players in translation had been very much physical things, where like you had to phone up people and send emails, and they had offices and people were bound. Like if you wanted a translator from say Italian to Chinese in microelectronics, then presumably you would have to speak to a translation agency and they would actually have a translation from Italian to Chinese. Maybe they did consumer electronics and not microelectronics, but they would fit the job nonetheless. And so you had this whole sort of, like both intermediation and sort of complication of having to find the exact most qualified person that was fit to do your job in the industry. Translated came in and sort of disrupted this thing with disintermediation. And these days, some people rank us better than Google. We're smaller, but we're better than Google, another main player, which is AWS and Microsoft for this kind of, for the machine translation part, okay? Because we also sell machine translation services. And we do a lot of stuff. We have 200 languages, we have 200,000 translators as well, and we've developed our own machine translation system that we use these days to help our translators, and the business goes well. And we signed the world's largest contract in translation in the history of I must qualify this, the largest known private contract in the history of translation. The number is public, so I can tell you it's 120 million euros, no dollars, with Airbnb back in 2021. So it's the largest known single contract in this history of translation. Qualifiers are in order because we kind of think that they won't tell, obviously, but that they were defense projects in the US where maybe the amounts were bigger, but we don't know for sure. Anyhow, an interesting piece of data that we have collected over the years, I'll show you now. No. Can you start the video? No, there isn't any audio. No, it's just a loop of a video loop. Let's see if it comes up. And if it doesn't, then I'll just show you a curve. Okay, so this is a plot that shows here is just time, okay? It goes until October 2028. And here's a number. I mean, it plots a single number, which is unit is seconds per word. And it's a plot we've been documenting for a long, long while. This is January 2015. So it's the number of seconds that our human translators spend post-editing machine translation, okay? Proportional to words, because we know that if they need to post-edit 20 words, they spend about twice the time they need to post-edit 10 words. And so we've been measuring this thing, this time to edit. And as you can see, it goes nicely down, as you would expect. This is due to the to technical progress in machine translation, essentially, because it's the time that they still need to spend on the thing until the translation is deemed to be, yes, I know, of perfect professional quality. And the interesting, obviously, that goes on here is what happens here. So you need to understand that the blue line is not exactly zero, because translation works like this. If you take the translation that's been made by a professional and you give it to another professional, not telling them it's been a human, but it's a machine, then they will still spend some time post-editing it, clearly, because that's called preferential edits. So they're going to do preferential edits. And how much time does it take them to read, ponder, type in the preferential edit? Well, that's about 1 second per word. We know that because we've done experiments. We wanted to know. And so the interesting part is here, because that's where you become superhuman. So when the line, the orange line crosses the trend line, crosses the blue line, that's when you're as fast as the quality that you can get out of another human. This is unrelated to my talk, but I just thought it's a really interesting piece of, analysis that you can read up on our website. There's a blog post about this. And anyhow, I'm moving on. The other thing that I do is PySchool. So PySchool is a school of AI, and we have a program there called it's Pi School of AI. Several times a year, as it says, we take on AI engineers, so people with a background in AI, who want to try their hands at industry projects. It's a bit like an internship, but in a much condensed form. It's 8 weeks. We source industry projects from companies who sponsor the entire thing, so it ends up being free to people who participate. And we apply state-of-the-art AI, stuff that's been published on arXiv like 6 months before, or that's come out on GitHub libraries 6 months before or so. And we solve that one business problem, okay? So this is a really nice thing that we've been developing for like almost 7 years now, ever since I started in 2017. And we've now done 100 challenges, 100 projects with this, and trained 200 fellows, we call them, so that's AI engineers. It's a sizable community already. And we've got really great people on board helping us. So these are scientific board. They're all veterans of AI. But let me, I didn't even start my watch, so I don't even know how much time I've got. Cesare, can you help me with time? Where do we stand?
Yeah, you have 11 minutes plus 10.
20 minutes.
20 minutes.
Thank you. Excluding questions.
No.
Excluding, yeah, that's what I was. And then all of this happens within PyCampus, which is an investment fund. So PyCampus invests in mostly applied AI startups. We've got 58 investments to date. We invest at seed level, so that's 50 to 500K euros. So if you're a startup or a founder and you want to check if we'd like to invest, then come and knock on our door and we look at stuff. Let me speak of the project that I want to tell you about, and especially why foundation models for speech are so important here. So this is an EU project that we got money from the European Commission. It started in January. It's a 7 million euro project. It will last for 4 years, and we've got 8 partners on the project, translated leads, so I'm the project coordinator. And what we're doing on this project essentially is we are building avatars for video conferencing, like you're starting to see somehow in some video conferencing platforms these days, except we want to bring it further. So one type of other, so imagine this is a video conferencing room or table, and you've got some physical people. And then you've got this guy here who we call Butler. This is a kind of meeting secretary. It's an agent, an avatar, an agent that does minutes, that catches up people when they enter the meeting and they're a bit late, that does summarization, therefore, that does agenda keeping and post-processing and stuff. And then there's another kind of avatar, which we call the agentar, which stands in for people who are absent from the meeting. So you can't, because of time zones or because you're booked on 2 meetings or whatever, you can't attend that meeting, so you send in your agentar. And they represent you because they've got knowledge of your private or your corporate data maybe. So in theory, we want them to be able to solve the ethical problems related to having access to your very private data, which is in your emails and stuff like this, and also represent you, so kind of embody your image and maybe your voice as well, and all these, thorny sort of social and human factors, not to speak of ethics and legal questions. So this is what we'd like to do in Metween. And the entire thing should be seamlessly multilingual, so that means there should be all sorts of speech technology going on here, real time, speech not only from the audio point of view, so not just speech-to-speech translation or subtitling, dubbing and that kind of stuff, but also the video part of it. And by that I mean lip dubbing, which means redrawing in a sort of realistic way the shape of your lips when your speech has been dubbed. Stuff like voice cloning in the audio domain pertains to that as well, of course. And then let me show you more examples of what is speech and what we're speaking of here. So speech is all that stuff. It's the audio. It's what happens at the language level, okay, so stuff that we usually in data find as text. Then it's also the video part, which gives access to all the rest that speech is made of, what I'm doing here. Stuff like gestures, like head movements, or like gaze where I look. You're starting to see video conferencing platforms start taking care of gaze parallax, which is the issue that you have when you're looking at your screen, but the camera is there, and so you've got, people have got the impression you're looking elsewhere. And this is the very start, of taking care of all these aspects of the human-to-human communication that we really want to get right if we want to have this sort of totally immersive video conferencing experience. So this is all that goes on in speech. And here I've just listed on this slide, I'm not going to go through the details, what's going on at different levels of the speech phenomenon taken very, very broadly. So it goes, I spoke of a few. Speech audio is far from solved, if you ask me. So we obviously see a lot of stuff that's speech transcription and text-to-speech, that's nice. But speech is a lot more than just this. Obviously prosody, melody of speech, kind of taken care of already. But stuff that is non-verbal, that is disfluencies, or what linguists call phatics, so stuff that I say, which obviously happens a lot in video conferencing, or like stuff, this kind of stuff happens in real life, and we want to be able to take care of all these. And then video and all the, cultural aspects of movement, all this All this is contained in that. And so foundation models, why foundation models? So maybe you've seen this picture before. This is from from one report from the Stanford Center for Foundation Models that was established for the study of foundation models. And it's a thick report that they published in 2021, and they've got this very interesting color palette I found throughout the report. To explain what a foundation model is. So a foundation model is essentially a very big model that is pre-trained and that uses transfer learning to be able to execute a range of what's called downstream tasks. So the idea is transfer learning everywhere. Is that you got this big pre-trained thing, you fine-tune it, that's the paradigm of foundation models, to execute downstream tasks. And let me see. If we speak of LLMs, then let's take a moment here to discuss exactly why they, in how far they are foundation models. So we know that there are very many downstream tasks to LLMs, be it only because there are papers like this, because this is how the entire thing started. GPT-2, the paper, language models are unsupervised multitask learners. That was the very point of LLMs at GPT-2 time. And then we've got, on top of that, we've got benchmarks. And benchmarks contain so many tasks that the performance of a given LLM can be measured on. Not all having to do with dialogue, but many having to do with text comprehension, summarization, answering questions, and all the stuff that you know. This is Helm, this is MMLU. So MMLU is a huge benchmark that is used these days for LLMs, and it contains like about 50 sub-evaluation sets for all the tasks that LLMs can carry out. So back to the slide before. So there's this downstream task and fine-tuning element. Okay. There's this pre-training element with naturally occurring data, which in our case is running text. And then obviously I want, in the slide after, I'll make the parallel with what happens in speech. But in LLMs, this is what happens with text, and that makes them foundation models for text. And then we've got, well, different techniques for fine-tuning and different ways of fine-tuning. And it's getting a bit more technical, but is really important, in fact, for the design and for solving the foundation models problem from a technical point of view, is this stuff with auxiliary tasks and losses. Who here knows what a loss is in the context of neural networks and neural network training? So just want to make sure I've got everyone on board. So if you're unsure maybe, then the loss is the thing that during neural network training, you're bringing down. So it's a quantity, it's a mathematical quantity. Generally, it resembles something like an error, and you're trying to bring this down by changing the weights in your model, okay? And that's what training really is. It brings down this one quantity, nothing else. So especially, this is not to be confused with the downstream tasks. So you could say that performance in the downstream task is an indirect consequence of bringing down the loss, which itself is connected to what's called a pretext task. I call this an auxiliary task in this line here, but the technical name is a pretext task. It's a task that, in the case of LLMs, is merely next word prediction. So I'm speaking of GPT family models here, and I think I'm even mentioning these. Yeah, GPT family models, decoder-only models for those in the know. The task is literally conditional, so history conditional, next word prediction, also called causal prediction, and the loss is cross entropy. It's a classification loss. So we calculate the loss on the prediction of that one. Well, it's not actually word, it's token. Okay, but whatever. So that's what happens in GPT family. And just to make a parallel, there are other large language models, the BERT family of models, which are encoder only, and they've got slightly different pretext and loss designs. Namely, for BERT family models, what we do is we do masked language modeling, so we don't do next token prediction, but masked language modeling. The definition, the mathematical definition of the loss is again cross entropy, simply because it's a classification task. But then we've also got sort of techniques baked into the task, which is stuff like word masking or noising. So masking means replacing by a mask token. Noising means replacing by another word, but it's still a word from the vocabulary. Okay, and so this is to set the stage on what LLMs are in terms of being foundation models. And so taking all this to speech now, and how much time I got? 10 plus, okay. So similarities and differences with LLMs and foundation models for text. So what looks very much alike when we're trying to design these things, we've got plentiful unlabeled speech data. It's just audio of speech. And in a couple of slides, I'm gonna speak about video. Video is another source of unlabeled data because it occurs naturally. And generally, when you've got video of a speaker, you've also got the audio of the speaker. At least this is the way that video data comes up on the internet, most of it. It's in sequence form, just like text, well, because it's language, and you've got the text layer that's kind of synchronous with the speech, clearly. So you can do some self-supervised training, and there are many tasks that are naturally attached to the usage of speech. So translation is one, transcription is one, so text to speech, speech to text, speech to speech translation, speech to text translation, everything you can imagine around this. Differences, however, text didn't have this thing where you have two modalities that correspond to one another. Speech is intimately connected to the text layer, okay, the transcription of this thing, because at the end of the day, speech is what we generate based on schematically some idea of the text we want to say, the words at least. It's a bit more complicated than this, obviously, because all the prosody and, for instance, the gestures and the emphasis that we give, this is not exactly encoded in words, but hey. So this is a bit different with speech. And then we've got, it doesn't look the same from a signal point of view because text, well, it's characters, right? And therefore tokenizable easily. Speech, continuous signal, you can sample it, you've got all the stuff that you know from signal processing. But then what you need to do is you need to generate window speech. So in many applications, you have 20 millisecond windows of speech because this is the time scale at which stuff happens in speech. But then those continuous speech observations, they're dense, they're continuous things. And so often enough, you'll want to discretize them. So this is something that did not happen this way, at least in text. This is a bit different. And I'm going to skip over these things because I now realize that I've got more material than I will have time for. So people who've worked on foundation models for speech are the people out at Meta. So this is work that they did in August last year. And the dates I've got because this is, well, to say how recent what is. So this work is quite recent. In the meantime, they've done version 2 of this Seamless project, which I encourage you to look up. It's very interesting. It's a huge project. They've got at least 50, maybe more people working on it. The report that they've published is 145 pages and stuff. It's a lot of fun trying to understand what's going on. And it's a project that works exactly on these tasks that I've listed earlier. The way it works is it tackles this thing that is, it centers around this thing that's called representation learning, which is, let me see if I can pull out this slide here. So representation learning is a sort of, it's a task that you need to tackle to do foundation models. It's a sort of abstraction of the signal that you need to produce in order for your model, your neural model, to manipulate something that is sort of low dimensional, that is easy to manipulate, and that has lower complexity, lower bit rate with respect to time than the original signal. And so representation learning in speech is one thing that can be done. So here you've got a model, an example of such a representation learning model, UBERT, from 2021, that does exactly this. I can explain very quickly how it works, and you'll understand it immediately. It works from unlabeled speech, just speech, a lot of speech. Maybe some of you have heard of Wave2Vec. Wave2Vec is another representation learning model, and does something very, very similar. So both what they do is they learn in a self-supervised way using, and this is where it comes in, a masked loss. So they learn to sort of guess what is in the middle, a bit like BERT family LLMs. They have a mask loss. They take in some speech audio, and then they discretize, window it, and build some represent like vectors, dense vectors here at that level. And then what they do here at that Z level layer is they cluster the things that are in the middle here, so that here at that level, the unit representation of these speech windows will be from a vocabulary of, in their case, Hubert, it's about between 100 and 1,000 units. So there's just a dictionary of 1,000 units to represent any speech. Okay, so this is if you look at the bit rate, this is a highly compressed representation of speech. Okay, that is then put into use. Let me see in this model here. So this is something that abstracts. It's something that abstracts and then is used to do both speech recognition and also at the output level speech synthesis. Thank you. The sort of data that Seamless M4T, that's the name of the model, uses, you can see from the list, a lot of this, the largest part actually is unlabeled data. It's the cheapest you can get. And only a tiny fraction is labeled data. And this is obviously for the reason that I'm trying to illustrate on this slide here, which is that when you look at the cost of data for these different tasks, text-to-speech, speech recognition, machine translation, you ask humans to do the task or you ask cloud APIs to do the task. This is the factor that the human effort costs more than the cloud API. So this factor of about 1,000, 2,000 is the very reason why when we look at the makeup of the data sets of models such as Seamless, we're going to see similar distributions in terms of the amount of data that they're using of one or the other sort. I'm going to skip that, guys. Another foundation model for speech, but this time oriented more towards generation, is this voice box thing, again from Meta. I swear I'm not doing any advertising for Meta, but it's true that they're doing a lot of work in this area. Voice box. This is another type of foundation model, and it carries out different tasks in speech synthesis. So it does tasks like denoising, TTS, and then it can do voice cloning as well. So this is why essentially being built on the same building blocks that I mentioned earlier, you can do all these tasks with that. So in essence, with the magic for doing these foundation models, and this is what we're starting to work these months in Metween as a research project, is these losses. It's the exact definition of these pretext tasks, and the definition of these losses and the recipes that goes around defining the exact combination of data, the pretext tasks that fits the kind of data, and the loss that you can define around this. Next step, and so you could argue, that a lot of what I've spoken about is stuff that already exists in research, but this is the next step. Obviously, this is what we want to tackle in Metween. It's the video part. So this is an old GIF from NVIDIA. It's from 2021 already. And if you remember the different modalities, well, the argument for doing video is that with video we can access all the other stuff that goes on in speech production that we can easily record on video, but it is cumbersome to measure in different ways. So audio, obviously the only way you can record it is with a microphone. Okay, thank you. But mouth movement, gaze, you could imagine some complicated machinery to do this. Forget it. It's obviously efficient, cheap, and the right way to go to do all that on video, which is why we're going to have a lot more fun with video than we've had with audio. Yes. And already people are starting to work on this, not surprisingly. So there's AV Hubert, which is the audio-visual version of this Hubert thing that was initially only for speech. People are now applying it to audio-visual signal. Here you have the audio, windowed. You have the video part. Same idea. You mask, and you're trying to guess, the model for training is trying to guess, so what is the shape of the mouth here? What is the pixel distribution here? And then they compute a loss on the guesses, on the predictions, versus the ground truth. So same story again. Clever configuration of losses and of tasks, and you get a representation learning system for audio and video put together, the two modalities here in this case. And it goes on. So very early, this is a couple of days ago really, you had this model come out from a Korean lab from KAIST, and what they're doing is essentially an original take, but it's gaining traction on foundation models where as part of the backbone, you're using an LLM, and you're using the fact that the LLM can do in context learning, it can be prompted. And so here the trick is that you will, a bit like you're seeing in, say, GPT-4v, for instance, in the same backbone, the same LLM, you'll feed embeddings that come from, partly from text prompts here, this part is a text prompt, and partly from an encoder, which is exactly the AV Hubert we had on the slide before. So you're building the sequence of embeddings. It's not tokens of text, and instead it's tokens that come from the audiovisual encoder. So it's this part here. So you take this as a frozen element. This is from AV Hubert. And you fine-tune what's going on at this level here. You fine-tune your LLM so that it's able to essentially absorb not just text tokens, but also audio-visual, i.e. video plus audio channel tokens. And then you prompt it, so that is, trick here is you encode the task in the prompt here, just like you do with an LLM, but sometimes we forget that the LLM effectively somewhere has an encoding for the task, which results from our prompting it with a definition, a verbal definition of the task, and that people are actually looking at exactly, so in a paper just 2 days ago, so I find this really cool, where in the LLM is the task encoded. So for instance, you ask it to do machine translation. In what place in the LLM is there some configuration of neurons or of activations really, that make it so that the task that is going to be performed is machine translation, as opposed to, summarization or anything. And so this is exactly what's going on here with this type of model. So we're getting there in a way. We've got a lot of challenges on the way. This is, our project here is for 4 years, so we know that architecture is just one piece of the equation, finding the right type of data, pre-training recipes, the fine-tuning procedures that we're going to use to go from a foundation model to the downstream task models. This is going to be interesting as well. And then obviously, how are we going to use it in applications? And here, just for fun, I copied the conclusion of the Seamless M4T report at page towards the end somewhere. And they point out that exactly, this is one thing we're not touching. Beyond spoken and written languages, the visual modality and cross-lingual communication, blah, blah, should be tackled. This is really what they're also going to work on. So it's going to be interesting seeing what comes out in the years to come, in the months to come. So we're going to work on this inside this research project. We're going to open source and release almost all of our outcomes under open source licenses, so weights, training recipes, data, so MUMO-SPI, multimodal speech is the name we give to our data set. This is also something that's going to come out of the project. And if you're really interested, then come and join us, or if you've got friends who are really interested in this kind of stuff, come and join us. We're looking for people to join our team here. And if you want to stay updated, then follow us. Thank you.
Thank you, Sébastien. A lot of stuff, very interesting. And any questions? Okay. Please speak.
Thank you. Very interesting talk. I was every day, I open X and I see very cool demos of speaking agents and stuff like that. Okay, I think every one of you do. I was thinking, in your opinion, how much time do we need to get to viable real-time conversation across, like, for example, imagine a salesman agent, okay? We've seen cool demos of stuff like that. And in your opinion, how much time do we need to get there, and what are the most difficult challenges? Because, you know, latency, of course.
So you're saying artificial conversational agents?
Yeah, artificial conversations, where, for example, a salesman collects from you, like, information and stuff like that, and then it builds directly an offer,
Okay.
for example.
Totally artificial, no human behind. Totally artificial. Your hypothesis is this is totally artificial. It's a system. There's no human behind.
Yeah, exactly. And so latency, of course, is a big issue, you know, because when you're speaking. But what are other challenges? And how? But my question is, how much time do we need to get there? It's like 6 months, or it's more like 3 years? In your opinion, just it's a guess, of course.
My opinion is more like 3 years in production. And because I know, because in the industry, you know how much work it is to get things to production. And I think even I would say that most of the obstacles are maybe not going to lie to get to sort of demo level, but probably rather overcoming all the obstacles that have to do with acceptance and with getting the small increase of quality, or, well, no, the last mile in quality that makes it so that this is acceptable to consumers, as opposed to being totally rejected and banned and people getting angry and everything. So I think this is going to be longer than people expect, because people tend to look at demos and see what goes on in industry labs, and you have the impression that this is, the week after next, but actually then there are a lot of privacy issues, infrastructure issues, cost issues as well, because compute is a factor in these things, just like cost is an issue in like marketing in general, or in marketing campaigns. When you have SMS campaigns, or you have robocall activities, then, well, you need to decide how much you're going to spend on these activities. So compute cost is going to become an issue as well, and I'm leaving aside the regulatory issues, and there are going to be a number of these having to do with these systems, I'm sure, and not all of these are sort of solvable in research. Okay, so a lot have got to do with turning research into products. This is my point here.
So for you, it's more like an engineering problem than
even more than engineering. It's a product problem.
Yeah. Okay.
Product design problem.
It's not like that there's some kind of limit, scientific limit that you see in getting
the
like
scientific
so much
bits. We're getting there.
Okay.
Where there's this work, other work, we're getting there. Compute,
okay,
we're getting there.
Okay, thank you.
Data, well, someday we'll have exhausted all the data we can actually fetch from the internet. Very soon, actually, probably. So we're gonna have to invent some cleverer, smarter data recipes or ideas to work with the same amount of data, because we're not going to be able to get more data, unsupervised, unlabeled data, that I'm saying. And so this is going to be issues as well. But as I'm saying, the scientific ones, I think we're gonna solve first, certainly.
Okay, I got a signal that we have no more room for question, but it depends on your plane schedule. You can take one more, or
I can take one more if you let me, and then we can take them
maybe there are
outside.
people going outside and drinking beers, and we are here.
You're the MC, Cesare, you tell me.
Yeah, okay. One more question, come on.
There you go.
No, I was interested about the chart you were showing about the linear trend of translation.
Okay. Yeah.
Do you think it will actually continue with the linear trend, or it will like asymptotically go to the human translator threshold, because like people just like people just like to change stuff because they have preferences?
So you're saying,
or you're just are gonna stop
evaluating. This is a different take on the same plot. Is this going to go through here?
Yeah, if it's gonna go through or just asymptotically, or you're just gonna stop giving to human evaluators the translations.
So I have a hunch that we can go below the blue line, which means we can make translations that are so good that humans will just give up on trying to post-editing them. And so you will actually go superhuman on machine translation. That's because I'm an optimist, maybe. But it does happen in some, in AI, superhuman certainly does happen. In this case here, the one thing that makes it hard to go sort of superhuman is that the evaluation itself is done by humans. So that's a bit tricky. And also most of the parallel data obviously is produced by humans. So it makes it a bit difficult. You need to sort of define the task properly and whatever. But I think it could happen. Just like I think, this is a bit science fiction-y, but I don't think it will stay for long. Dialogue, verbal dialogue, okay? So imagine one day we'll probably have Turing test style agents that are undistinguishable from machines. We certainly are there in many settings. And undistinguishable is one thing, but nothing really prevents a system that has got much more memory, higher speed, higher computational capacities than human brains, less ego, whatever, all the things that humans have that block them or that speed them down. A system will, not having all these things, I believe, can have superhuman capabilities in dialogue, which is to say, for instance, people will just love having, ordering their pizza through this agent as opposed to any sort of human. Or the dialogue agent will be incomparably faster than any human in eliciting whatever information from humans. Or it's just that people will, in sort of market terms, they will want to use these systems. So I think that dialogue, we're going to see, and it's going to be a bit surprising maybe at the beginning, but I think we're going to see that systems will be superhuman in terms of their capabilities in these terms also. So I think this answers your question in a pretty comprehensive way. Thank you.
Okay, I will stay all night listening to you, but guys, the RAS signal and okay, that's all. That's all. Thank you. Thank you very much. Thank you, Sébastien.
Thank you.